All right, today we're going to be talking about slope fields. So the first question that you're going to come up against, and you're probably thinking, what the heck is a slope field? And so that's what we're going to address first, and we're going to use our background with differential equations to talk about this. So a slope field is a graphical representation of all the possible solutions to a differential equation. So it's basically an graphical antiderivative. So let's think about this differential equation right here. Dy dx is equal to 2x. This would be fairly simple from our background now with differential equations to be able to solve. And so to solve, we would separate our variables, moving dx over to the other side, giving us 2x dx. And then we would integrate, giving us y is equal to x squared plus c. All right, so now let's think about this for a second. Y equals x squared is a parabola with the vertex at the origin. Now, the transformation of the plus c just takes that parabola and it moves it up or down depending upon what that c value is. So this equation right here is not just one graph, because we don't know a point that is on the original function called your initial condition. We don't have that point, so all we know is a general solution. A general solution will have this plus c, which means our graph might be right here, our graph might be up here, our graph might be down here. One thing that they all do have in common, however, is that the vertex for that parabola is going to be on the y-axis. So what we're going to do is we are going to try to generate some kind of graph that would give me a picture of what all the solutions would look like for this differential equation, or for this general solution right here. But the graph is going to be called a slope field, and it is going to give us a graphical representation of the antiderivative of this differential equation. All right, so what we do is we take this dy dx and we think about points that are on our graph. So if I think about the point 0, 0, let's just start with the origin right here. That point has coordinate 0, 0, where the x value is 0. If I put 0 in for x right here, that means dy dx would be 0. What that means is that I would have a tangent line that would have a slope of 0, which would be a horizontal tangent line. So that's what I'm going to draw at that coordinate. It's just a very little tiny segment that has a slope equal to this 2x at that coordinate. Now, let's pick some other coordinates. This coordinate is 0, 1. Well, 0, 1 has an x value of 0, which means dy dx would be 0 there also. Well, that also means that every point on this axis would have a slope of 0, which means these tangent lines would all be horizontal tangent lines. All right, so let's pick another point. Let's pick the point 1, 0. Well, at 1, 0, that means your x value is 1, so dy dx would equal 2. Well, what I'm going to do then is draw a little tangent line that would have a slope approximately of 2. And what you can see is that rise over run, up 2 and over 1, this line is going to kind of point at that point right there for a slope of 2. Well, what you'll quickly recognize is that every point on this vertical is also going to have a slope of 2. So at 1, 1, you're going to have a slope of 2. At 1, 2, you're going to have a slope of 2. 1, 3, you have a slope of 2. And so it continues up as well as down, because your x value at all these points is 1, giving you a slope of 2. Well, now if you think about negative 1, 0, the x value is negative 1, and so when you put negative 1, that's going to give you a slope of negative 2. All right, so at negative 2, for a slope, we would draw a little tangent line that has a slope approximately of negative 2, and we do that here as well, and here, and all these points going up the same vertical because they all have the same x value. They're all going to have a slope of negative 2. All right, so what we would do then is we would continue filling up this entire graph with all these little tiny tangent lines. Now, as we move out this direction, our slope is just going to get more steep. As we move out this direction, also more steep, but in the negative direction. This is what your slope field actually would look like if you were to generate all this. And so you can kind of see from the curvature of this the outline of a parabola, going like this and then coming back up if you were to follow these tangent lines. Now you'll notice you would have a parabola here, because the horizontal tangent line means that you would have a minimum. So you could have one here going up, you could have one here going up, you could have one here going up, and so on. You could have them at all these different places, and that is because of the plus C. It gives us all the possible places where you could have that solution graph. All right, so let's take a look at the next differential equation here. This time we are not going to actually solve it like we did on the first one. We are just going to take a look at the slope field for this. Now, on the first problem, the only thing that impacted our slope was the x value. However, on this differential equation, the x and the y coordinate both will impact that slope of your tangent line. All right, so let's pick a point. Well, at 0, 0, if you put 0, 0 in here, you get an indeterminate form, which is not possible to evaluate. So that means we do not put a little tangent line segment right here. At 1, 0, your y value is 0, which also is undefined. So everywhere on the x-axis for this one, the slope, or dy dx, would be undefined. So we are not going to put anything on the x-axis. The reason for that is because your original graph might have a vertical asymptote, or a corner, or a cusp, or something, a discontinuity, something that causes that graph to not have a derivative at that particular point. All right, so let's pick a point. Let's pick the point 1, 1. All right, well, at the point 1, 1, your x value is 1 and your y value is 1. So that would give you negative 1 over positive 1, which is negative 1. So you're going to have a little tangent line with a slope of approximately negative 1. Now, if you pick the point 2, 2, you are going to end up with the same situation. 3, 3, 4, 4. These would all have the same slope because you're dividing a number by itself, giving you 1, and it's negative over positive, so it's a negative. Same thing is going to be true over here on the diagonal. Everywhere on the diagonal, you're going to have the same slope. Now on the other diagonal, if you pick the point 1, negative 1, well, if you put a 1 here and a negative 1 here, that's going to give you a negative 1 over negative 1, which is a slope of positive 1. So you get a little tangent line with a slope of positive 1. And that's going to be true everywhere on this diagonal. And then we would fill in other points. Similarly, I'm just going to go ahead and show you the complete graph of that. And this is what that looks like when you fill up all kinds of points on that particular slope field. And so with this, without even solving or separating the variables or finding a general solution, you are able to look at this slope field and determine, well, it looks to me like our solution is going to be a circle, because that's the pattern of our little tangent line segments. Now, we don't know the radius of our circle. That would be the plus c part. Might be a little circle here, might be a big circle out here. All we know is it's going to be a circle. Now, if we have an initial condition, for example, if I know that my graph went through the point 3, 0 as an initial condition, from that I could get a graph of my equation following the path of my tangent lines going around here. Not too bad for a freehand circle, okay? All right, so why do we need slope fields? Why don't we just separate the variables and solve the equations all the time? Well, we need slope fields because actually most differential equations cannot be solved. Therefore, we can use the slope field to determine the behavior of your antiderivative. You'll be able to see the curvature of your antiderivative even without knowing what the original function is. Okay? And especially if you have an initial condition, you can go from that point and follow the curvature of the graph. Now, there are some other means that are not part of the Calculus 1 course where you can get more precise with the graph of your antiderivative without actually even knowing what the equation is for that antiderivative. All right, so we're going to take a look at a free response question from the AP test a few years ago. This says to consider this differential equation right here, that y equals f of x be the particular solution to the differential equation with this initial condition. Function f is defined for all real numbers. A portion of the slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. So to start sketching the solution curve, you start with your initial condition at 0, 1. And see, from the slope field, you can see pretty much the curvature. So as I move to the right of this point, my curvature is going to move my graph up, and it's going to max out somewhere up here, and then it's going to come down because of our slopes. And so we can get a general curve going to the right here. And to the left, we can do the same thing. As we move to the left, we can see the curve is going to go downward. But then at some point here, it's going to turn and come back up. Okay? And that would give us a general curve for that solution. And we're able to get a pretty good curve out of that because of that initial condition, knowing exactly where that curve is. And like I said, there are some other means for being able to find more precisely points that would actually be on this curve. And you will talk about that in your next course with Euler's method, and then you also have some other methods that you will talk about later as well. All right, so part B of this same free response question says to write an equation of the line tangent to the solution curve at the point 0, 1, and to use that equation to approximate f of 0.2. All right, so we are going to start by getting the equation of the tangent line. A tangent line, you need two things. You need to know a point, which was given, and we need to know the slope of the tangent line, and we get that from dy dx because that means slope. We're going to evaluate this slope at 0, 1. All right, so at 0, 1, that's going to give us 3 minus 1 times the cosine of 0, which is 2. Therefore, our equation would be y minus 1 equals 2 times x minus 0. And that would give us, if we were to solve for y here, that would give us 2x plus 1 for our tangent line. Now we're going to use that to approximate f of 0.2, which means we're just going to evaluate this at 0.2, which would give you 2 times 0.2 plus 1, which is 1.4. And then part C of this question is asking us to find y equals f of x. So we're going to do what we have done in the previous part, which is separate the variables and solve for y on this. All right, so separating the variables, you're going to get 1 over 3 minus y times dy equals cosine of x dx, and then integrating both sides, you would be using u substitution right here and letting your denominator be u, where the derivative of u is negative dy. Well, that means we need to insert a negative here and a negative out front. So I'm going to go ahead and put a negative here and a negative out front, and that's going to work out then to give us a negative integral of 1 over u would be natural log of u, which is 3 minus y. Antiderivative cosine is sine, and then we got our plus c. All right, we're going to move the negative over to the other side. So that gives us natural log. Let's go ahead and let me back up for a second. We're going to use our initial condition before we solve for y to find out what our c value is. All right, so if we plug in 1 for the y value, that's going to give us negative natural log of 2. And then plug in 0 for the x value. That's going to give you sine of 0, which is 0, and therefore c is negative natural log of 2. All right, so now as we work this out, you're going to have negative natural log 3 minus y equals sine of x minus natural log of 2. Dividing by the negative, we're going to be solving for y here now, and that's going to give us negative sine of x plus natural log of 2. Exponentiate both sides, and so that's going to be e raised to the natural log, which is just simply absolute value 3 minus y, equals e raised to this power over here. Now, as we've talked about before, if you have e to the sine x plus natural log of 2, that can be thought of as e to the negative sine x times e to the natural log of 2. And this has a value of 2. So this becomes 2e to the negative sine of x. All right, I'm going to drop the absolute value signs now, which makes this a plus or minus. We're going to subtract 3, giving us negative 3 plus or minus 2e. And then dividing is 3 plus or minus 2e to the negative sine x. Now we do need to determine, is this going to be positive or negative? And we get that from the initial condition. If you put 0 in for x, we have to get 1 as a result. So if you put 0 in for x, it's going to give you e to the 0, which is 1, which means I need to use the minus, which will give me 3 minus 2, which is the 1. So our final answer then becomes y equals 3 minus 2e to the negative sine x. All right, so this is another free response question that was given a few years ago. And what we're going to do here is, on the axes provided, sketch a slope field using this differential equation. Now, what you want to do on this type of problem on the AP exam, my suggestion is make a table with x, y, and dy dx. Write down the coordinates of your points, which you have negative 1, 0, negative 1, 1, negative 1, 2, 1, 0, 1, 1, 1, 2, and so on. And then fill in your dy dx value according to those coordinates. So if you plug negative 1, 0 into here, the negative 1 gets squared, so that's a 1. 0 minus 1 is negative 1. And negative 1 divided by 1 is negative 1. So you get a dy dx value of negative 1. You then come over to your slope field, and at that coordinate, you draw a little tangent line with a slope of about negative 1. Now, the purpose of this table is so that when the AP grader looks at your slope field, if he has a question as to what the slope of this is, he can always look at your table and identify what it is you meant for that slope field to be. Okay. All right, I'm not going to fill in the rest of this. It's just a little redundancy. All right, so on this one, it says to find the particular solution, y equals f of x, for this differential equation. Go ahead and take a few minutes and use separation of variables to solve this. Go ahead and pause your video at this point in time. Okay, welcome back, and this is your solution. If you want, you can pause the video and kind of follow the outline here, narrowing it down to a solution of 1 plus e raised to this power by using our initial condition to determine whether it's plus or minus here. Now, what we want to do in this one, it says, for the particular solution, y equals f of x, described in part B, find the limit as x approaches infinity of that. All right, so what we had was y equals 1 plus e raised to the negative 1 over x plus a half. Now, if we think of x approaching infinity, this fraction is going to therefore approach 0. Well, if that fraction approaches 0, what's left is our limit. So our limit is 1 plus e raised to the 1/2 power. All right, so what we have are 4 slope fields right here and 4 differential equations, and we need to identify which slope field goes with which equation. And one of the things you want to look for are where your slopes are 0, where your slopes are positive, and where your slopes are negative. So, for example, on this first one right here, we can see every point on the y-axis. You have a horizontal tangent line, which means your slope is 0, or in other words, dy dx is 0. We have the same thing on the x-axis, which means your y value is, your dy dx is going to be 0 whenever your y value, for your y values. And so the equation that's going to generate that is going to be this one right here, where x times y equals dy dx. Because if your x values are 0, your slope is 0. If your y value is 0, then your slope is 0. So this one goes with your first one. On the next one, you can see that when your x value is 2, you're going to have a slope of 0 for these, because you have a horizontal tangent line, so your slope is 0 when your x value is 2. And the one that generates that would be this differential equation here. On the next one, we see that at 1, 1, 2, 2, 3, 3, 4, 4, and so on, you have a horizontal tangent line, so your slopes are 0 whenever your x and y values are the same. Well, the differential equation that generates that would be this one right here, where if x and y are the same number, when you subtract them, you get dy dx is 0. And then the last one here, one of the things you'll notice that's different about this one is that there is no slope field down here. And the reason for that is, obviously, this is our last differential equation. Remember that you can only take the natural log of positive numbers, and you cannot take a natural log of 0. So that means y cannot be 0 or negative numbers. So therefore, right here and everything below that, you are not going to have a slope field, because dy dx will not exist, because you cannot take a natural log of those y values.